slide shows representative researches concerning about traces of life. There are many reports already published, and some reports came from northern Canada, and some reports came from Greenland, some reports came from Australia. And in today's presentation, I'm just going to focus on the Isua rocks. And I have three different topics in today's presentation. In the first two topics, let me talk about more concrete evidence of early life at the 3.7 billion years ago. And in the second half of my presentation, let me introduce our discovery of boron-rich rocks in Isua. And this boron-rich rocks tells us many of things, and there are many implications of origin of nucleotide and the origin of RNA, and let me discuss about this problem as a third topic. This slide shows aerial photo. This slide shows aerial photo of western part of Isua. Those gray ones are the old rocks. They are 3.8 to 3.7 billion years rocks. They were formed on the ocean floors. The rest of the colored parts are just the lakes. There is one important report just came from this point. This one's done by Rosing. Here is Rosing. And he found this rock. And this is the black shell. This is metamorphosed black shell. And this is formed, this was the 3.7 billion years marine sediments. And this metamorphosed black shell contains abundant graphite. And this graphite has enrichment of carbon-12. Because of this kind of geological occurrence and also this kind of chemical features, he claimed that the graphite in those rocks are biogenic in origin. And many people accepted this conclusion, his claim. However, there is one problem. If early biosphere had already established that Isua age, we should see more black shell, and we should see more biogenic graphite in Isua. However, this was the only location. Therefore, we performed geological survey around here at this blue-colored area. Here is the conclusion. And we found black shell. We found another black shell. And this is published about 2 years ago. And Yoko Otomo, she was my student, and she found this black shell, and she examined the graphite in those rocks with a collaboration of Minik Rosen. Okay, this is the enlarged view of outcrop we found, and they look like black. And this rock contains graphite, reduced carbon. Here is the amount of reduced carbon, and we have abundant carbon, graphite in those rocks, up to 88%. This slide shows a microscopic photo of black shell, metamorphosed black shell we found. What you see here is some laminated texture here. And this kind of layered texture is most likely preserved sedimentary texture. And rock with this kind of sedimentary texture quite rare in Isua. And those white parts are they are representing rock components, silicates. And the black parts are the graphite. Yes, you see the visible graphite. Graphite is there. Before going to show some data coming from this graphite, let me introduce another type of occurrence of graphite in Isua. So in Isua, sometimes we see this kind of black-colored rocks. And this contains graphite, and this also contains the iron carbonate. Originally, this is described as banded iron formation. This was considered as metamorphosed marine chemical sediments. However, those authors examined this type of rocks, and they concluded that this is the carbonate vein penetrated in surrounding rocks. This came from later. And they also examined the origin of graphite, and they concluded that this graphite in those rocks were precipitated from hot fluids. They are not related to biological activities. Therefore, this rock contains no non-biogenic graphite. So this slide shows carbon isotope composition of graphite coming from non-biogenic graphite that I showed in the previous figure. And this is the carbon isotope data of coming from our black shale, metamorphosed black shale sample. In the blue plot, you see the range from -14 to -9. And in the red colored one, we have a range from -24 to -12. You see the contrast. And you see more carbon-12 enrichment features here. So this is quite similar to modern metamorphosed organic matter. So this slide shows high-resolution TEM image of graphite in the metamorphosed black shale. And this layer is representing the graphene layer. In general, this graphene layer is arranged very well, but you see this kind of rounded texture. I just call this is onion-like structure. And sometimes you see this kind of bending structure, bending texture here. And this type of structure is very common in the modern metamorphosed organic matter. Okay. So this slide shows STM image of graphite from metamorphosed black shale again. This time we are looking at morphology. Okay. So each of these one is the graphite grains, and this has the tube-like morphology. This has the hexagonal flake, and this is just a mixture of tube and hexagonal flake. And we see variety of morphologies. So this kind of heterogeneous form could be made from heterogeneous carbon sources, such as biomolecules. So if you have some single carbon source, you don't see this kind of heterogeneity. You see just one morphology, but we see the variety of morphologies. So we know the geological evidence. We have geological evidence. We have carbon isotope evidence. We have TEM image. We have this STM image. So all of the information indicate they are the biogenic in origin. So I would say it is quite sure that we had biological activity by 3.7 billion years ago. So let me move on to the second topic. So I was just talking about the metamorphosed black shale around here. So this black shale is extending to south, and if you go here, you see black shale, metamorphosed black shale. However, and this is the outcrop photo, they still have some layer texture, and I think this is the sedimentary layering. However, in this area, rocks are metamorphosed more. Rocks contain more garnet and also the biotite, and they also contain the graphite, and they are also the biogenic in origin. And those rocks are rich in tourmaline. Tourmaline is a boron mineral. They are rich in boron. That's what we found. This slide shows microscopic photo of garnet, actually the microscopic photo of thin section of the previous rocks. And this is the garnet crystal. This is surrounded by biotite and also the quartz. And if you see the inside of garnet, this is very dirty, and they contain lots of inclusions. And those, for instance, this or this or this and this, those ones, all of them are tourmaline. This garnet is full of tourmaline. In other words, this garnet is full of boron. So this slide shows the model of tourmaline formation. This is just a general view. And what we know is that we have metamorphosed black shale, and they contain the garnet. This yellow one is the image of garnet. They have many tourmaline inclusions here. So to have this inclusion, the garnet is a product from metamorphism, and the garnet had a precursor. The precursor was the biotite. And to make inclusion in garnet, we need to have tourmaline at the very early stage, before metamorphism. And biotite also had the precursor, that should be the clay minerals, and the tourmaline has precursor, that should be the borate. So therefore, we had some borate-rich environment here when marine sediment deposited on the 3.8 billion years ocean floors. So looks like we had borate-rich pore waters here. Then what's the significance? What's the meaning of this one? This figure shows famous mineral evolution model. Our data is against this mineral evolution model. Here is the geological age. Y-axis is the number of new boron minerals. So if you go to the modern age, you see a variety of more boron minerals. This is because boron is just recycling in the crustal areas, in the crust. And however, if you go to the deep time, old ages, almost nothing. So boron, essentially the felsic rocks, like a granite, is the source of boron. Some people interpret that at the old ages, the felsic rock was just missing. So therefore, there was no way to have a borate or a boron. However, our data, our finding, as a previous slide, like this, even at the early Archean stage, we had a borate-rich environment. So then, how do we have borate? How do we have boron-rich environment at the Isua age, early stage? So this slide shows the model proposed by the NHON, and this slide shows the tectonic model. Sometimes this is called the Proto-arc model to explain the tectonic evolution of Isua. I have two figures here. At the lower figure, this is the modern day style plate tectonics, and subduction is happening, and the volcanic arc is formed here. And NHON considered that some oceanic plates didn't subduct well, and they are fragmented. Those fragmented oceanic crust were accreted together, and they are making the thick crust. And at the bottom of thick crust, they are forming the felsic rocks. And I think this felsic rock was the essential source of boron. Okay? And this arrow is indicating the movement of deep fluids, crustal fluids, and some fluids are extracting boron from these felsic rocks, and they are carrying boron to the surface. And some borons are going to discharge into the ocean. They are creating the boron-rich environment. That's we see some boron-rich sediments even at the Isua age. Okay, so then the next question is, how do you connect this kind of a boron-rich environment or boron to the origin of life problem? So this slide, especially this slide, shows the chemical structure of nucleotide. As you know, nucleotide is composed of phosphate, ribose, and also the base. So we need to have prebiotic nucleotide to have life or to have RNA. However, we have a big problem. Problem comes from here, ribose, sugar. Because ribose is very difficult to make, and this ribose easy to decompose, and ribose is easy to convert it to other sugars. So many people made a struggle, and some people proposed that boron makes everything possible. Okay, this slide shows the proposed model to stabilize ribose. So here is a ribose, here is borate, and the ribose forms complexes with borates like this, or sometimes like this. Okay. This kind of ribose-borate complexes prevent ribose decompositions. By stabilizing ribose, this ribose can further interact with nucleobases, and they can make nucleoside. However, we need to have lots of boron. Small amount of boron doesn't work. We need a high concentration of boron. And there are many debates if we could have boron-rich environment on the early Earth. Some people say no, and some people say yes. As I showed in the previous, in the second topics, we could have boron-rich environment. So let me show the other type of experiment. This is the independent experiment. This is published a few weeks ago, and this is the new data. And boron, actually the borate, makes a different pathway to precipitate mineral if you are considering the evaporite basins. For instance, in the evaporite basin, you see calcium phosphate so common, and also the magnesium sulfate common, if there is no borate. But if the borate is present, you are going to see the calcium sulfate, and you're going to see the magnesium, boron, phosphate here. That is called Lüneburgite. So we consider that this Lüneburgite is very important when you try to make prebiotic nucleotide. So as I showed, the borate can stabilize ribose, and this ribose can attach with a nucleobase like this. However, there is still the problem, and we need to attach phosphate like this. However, there are 3 potential places to attach phosphate. Here, this is the one place, this is one place, this is the one place. We need to attach phosphate here exactly. That we hypothesized this mineral can do this right thing. And this mineral supply boron again, and the boron is attaching here, then only this side becomes available, then this phosphate is going to attach here. So this is the model, our hypothesis. To examine this hypothesis, we performed the experiment. So we prepared uridine like this, nucleoside, and we just put into the mixture of evaporite minerals, and we incubated a little bit. Then we analyzed the products, and here is the results. And most of the uridine survived. They didn't react at all. But we could produce the 5' UMP. UMP is a uridine monophosphate. That's a nucleotide. Okay? And we had sorry that I don't see clearly, but we see some products, but this product is the highest through these processes. Therefore, I would say we could make nucleotide by these processes. So this further implies importance of evaporite minerals to make RNA. Okay, this figure shows the modern day evaporate basin, evaporate environment. And this figure is the Death Valley National Park, California in United States. In this area, some volcanic activity supplies boron and also the phosphate. They are carried by river water, and river water is extensively evaporating, and they are precipitating some salt and also the Lüneburgite. So this is the textbook location to have evaporate minerals. However, the next question is, if evaporate environments were available on the Hadean Earth when the life started. So Isua rocks again tell us the information, important information. There was another important publication a few months ago done by the NHON group, and they found the stromatolite in the Isua. And this is the stromatolite look like rocks, and they have some columnar things, and here is another one. And this is important to report. In addition, they also claimed that this stromatolite was formed in the evaporitic environment, evaporate basin. So this is also important to claim. So therefore, we could have evaporate basin, even at the early Archean stage. I would say, why not at the Hadean? So this is the last slide. So this is the same slide I showed before. This is based on the Proto-arc model. So there are many ambiguity about tectonics during the Hadean period. But at least at the Isua age, at the early Archean age, we had this kind of tectonics, some kinds of tectonics. And this tectonics works very well to explain everything. For instance, the thickening of crust makes some very shallow area, and this is going to make some isolated basin, and some waters are evaporating. And probably stromatolite found by the NHON, and the stromatolite was formed around this kind of environments. And also, this tectonics could make TTG. It's not necessary to be a TTG, some felsic rocks, a source of boron. And we know that there are many Hadean zircon that was formed in the felsic rocks. So therefore, we could have felsic rocks around here. And some deep fluid extract boron to the surface. And if the boron reach here, you can make a boron-rich environment. So I would like to propose that the first nucleotide was formed in this environment, evaporitic environment. So this is the final comments from my presentation. We need to consider early tectonics. We need to consider early minerals also. And they provided suitable environment to stabilize ribose and then to form nucleotide and also the RNA. Thank you for your attention.